Hello, Namaste. This is Rohini Mergu talking about IMPATT diode. At the end of the video, you will be able to explain the construction and working of IMPATT diode. You will be able to explain construction and working of IMPATT diode, list the applications of IMPATT diode. Before we move ahead, let us talk about what are Avalanche Transit Time diodes. Avalanche Transit Time diode, the name itself consists of two terms, avalanche and transit time. So avalanche diodes are nothing but the oscillators which uses the carrier impact ionization, that is the avalanche effect, and the drift space, that is the transit time effect, for producing the negative resistance. What is negative resistance? Generally, by Ohm's law, as we say, V is equal to IR. As voltage increases, current increases linearly. But in negative resistance, even if we increase the voltage, the current is reduced. So this part is called negative resistance, where it is assumed that the device will be sourcing the energy instead of absorbing the energy. So in order we make the device to work in the negative resistance so that it acts as a source. So avalanche transit time diodes are designed in such a way that they will work in the negative resistance region. And they use the effect of voltage breakdown, the avalanche effect, as well as they use the effect of transit time. There are types of avalanche transit time diodes. One is IMPATT diode, where it is impact ionization avalanche transit time diode. TRAPATT diode, trapped plasma avalanche triggered transit time diode. BARIT, barrier injected transit time diode. Let us look at first IMPATT diode. IMPATT is impact ionization avalanche transit time diode. It is a high power diode. It is made up of silicon carbides with high breakdown fields. Its operating frequency is 3 to 100 gigahertz. It is used in low power radar systems to alarms. These generate high level of phase noise because of avalanche process. So construction of the IMPATT diode is like this. It's nothing but a wafer, semiconductor wafer. It is generally of gallium arsenic, silicon, germanium, indium phosphate. These can be used for construction. But here it has heavily doped P region on one side and heavily doped N region on the other side, and in between there is a drift space and small avalanche region is shown. And these diodes work in the avalanche region so that they are reverse biased. So you can see that N is connected to positives of the supply, P is connected to negative of the supply. So these diodes work in reverse biased condition. However, gallium arsenic is preferred over the other wafers because of low noise behavior. This is a construction of IMPATT diode, where you can see this is the wafer here, which has N structure here. You can see it is a P plus heavily doped and N plus heavily doped region, and in between there is a drift space, and this gold wire contact is taken out from here. The leads are taken out and it is placed, heat sink is there, and this all is put in the ceramic housing. Let us look at the working of IMPATT diode. IMPATT diode works on the principle of avalanche breakdown and transit time delay. It operates on very high voltage gradient around 400 kilovolts per centimeter. So when we provide such high reverse bias where it generates 400 kilovolts per centimeter, then it produces avalanche current. Our normal diodes break down in the avalanche region, but IMPATT diodes are formed in such a way that by adjusting the doping concentration so that it will not break down, rather it will produce avalanche current. An action that causes the abrupt increase in the junction current in the reverse bias condition of the PN junction diode, leading to junction breakdown, which is called avalanche breakdown. In reverse bias condition, the width of the depletion region become extremely thick, as we know. there is a depletion formed in the reverse bias condition, and in the reverse bias condition we are providing very high voltage, high reverse bias, so that very thick depletion region will be formed. And when there is a reverse bias, the minority carriers start moving across the junction or drifting across the junction, and these charge carriers, when provided with a high voltage gradient, in such case large number of mobile charge carriers which with minority carriers are generated, which moves with a higher velocity or greater velocity. As they move along the junction, these high velocity carriers collide with other atoms in the crystal and they generate electron hole pairs. Now this causes multiplication of charge carriers. As they are colliding on the other minority carriers, they are generating hole pairs. They knock out the another charge carriers. So such a process goes on multiplying, and it is called as a multiplication of charge carriers. Thus, moving the charge carriers generate high current inside the device, and this is the avalanche condition, and the current produces avalanche current, and the process is called as impact ionization or avalanche. The same I can explain here. We have provided high reverse bias up to this DC and small amount of RF when it is applied. See, what happens is, due to impact ionization, the current pulse or avalanche current pulse will be produced inside the wafer, but this pulse will not appear at the point when the voltage is positive. This pulse will appear at a point when the voltage is 0. Because avalanche is a multiplication process and it is not instantaneous. The process takes time. As a current pulse is maximum at the junction occurs at the instant when the RF voltage across the diode is 0 or negative. Okay, fine. So we get 90-degree phase shift between voltage and current. But what we want to achieve? We want to achieve negative resistance. That is 180-degree phase shift between voltage and current. So with avalanche process, we have obtained 90-degree phase shift. So another 90-degree phase shift that we expect to work the impact diode in the negative resistance region can be obtained by using the drift space, by adjusting the drift space of the impact diode. So the current pulse is situated at the junction and it will not stay there, and the current pulse will move towards the cathode. The drift velocity dependent on the presence of the high DC field. The time taken by the current pulse to reach the cathode depends on the velocity and the thickness of the highly doped N+ layer. The thickness of drift region is selected such that the time taken for the current pulse to arrive at cathode corresponds to will provide another 90-degree phase shift. So total we get 180-degree phase shift between the voltage and current. Voltage is negative maximum, current is positive maximum. Let us look at the advantages and disadvantages of impact diode. Advantages: it provides high operating range. It shows compactness in size, very small size. Impact diodes are very economical compared to others. They provides reliable operation at high temperature. The disadvantages: the rate of generation of electron hole pairs is in the avalanche region causes the generation of high noise, because avalanche is a noisy process. So the device is noisy. It offers low tuning range. Tuning range is less. It offers high sensitivity to different operating conditions. Let us look at the applications of impact diode. Impact diode finds applications in microwave oscillators, in parametric amplifiers and microwave generators, in intruder alarm systems, as well as impact diodes are used in telecommunication transmitters and receivers. These are the references used for preparing this video. Thank you.